All right, we're back. An analog voltmeter is used to take measurements of a constant potential difference across a resistor. Remember that potential difference is voltage, so it's like voltmeter measures volts. For these measurements, describe one example of a systematic error. We've talked previously about how a zero error is a type of systematic error. If the voltmeter is to the left or to the right of zero, then all of your readings are going to be off, and so you can correct that by recalibrating it. I showed this is an example of an analog voltmeter, right, that actually has a needle. And so right now you can kind of see that it is basically on zero. Maybe it's a little bit above it. And so that would be an example of a zero error. A random error, okay, a random error. A random error we cannot eliminate, but we can minimize. And we've talked previously that every time a human being makes a judgment, uncertainty is introduced. And so again, if we sort of look at this, you're always making a judgment about where does the needle sort of match up to a line there, right? And so some people might, sort of make a judgment, oh, it's like halfway in between those two, or other people, sort of might, sort of make a different judgment. So there's a little bit of uncertainty there. And so by reading the instrument, that could be a source of random uncertainty or random error. Let's take a look while we're thinking about it. What does the March state say about that? They give examples of zero error or wrongly calibrated scale. They say reading the scale from different angles or wrongly interpolating between scale readings or divisions. All right. So reading the scale from different angles, that's called a parallax error, wrongly interpolating between scale readings / divisions. And so again, sort of making a judgment, between two sort of marks, you can say, well, the needle sort of looks like it's in between, these two here, so you could sort of do that incorrectly. That would be an example of a random error. All right, the reason why we had this question paper queued up was to take a look at the practice working with uncertainties. And so we have the potential difference across the resistor is measured as 5 volts plus or minus 0.1 volt. The resistor is labeled as having a resistance of 125 ohms plus or minus 3%. We want to calculate the power dissipated by the resistor, calculate the percentage uncertainty in the calculated power, determine the value of the power with its absolute uncertainty to an appropriate number of significant figures. Those 8 marks, I feel like, would have been really tough to earn unless you're very well practiced doing these types of calculations, because here we don't just have to sort of remember how to combine uncertainties and things. We also have to know something about the sort of electricity, which you may recall from your previous studies of physics, but it's not something that we've reviewed yet this year, right? So that makes it a little bit trickier of a problem. All right. Calculate the power dissipated by the resistor. So let's start, with that one. We have the resistance and we have the voltage, right? So power is current times voltage. That's one of the ways to sort of think about power. Just as a quick review here, current is the rate of flow of charge, and so it's charge per time. That's what current is. The intensity of the current is charge per time. Voltage is the energy per charge. Energy per charge. And so we multiply current and voltage, we're canceling out charge, and we get energy per time, which you'll hopefully recognize as one of the ways to think about power. The rate that one form of energy can be converted to another. Like power is work over time, work and energy are the same thing. So that's a good equation for power. Ohm's law tells us that voltage is equal to current times resistance. It's one of the ways to think about Ohm's law. Sometimes we'll see it like R equals V over I, or we could rewrite it like I equals V over R. All 3 of those are good ways to think about Ohm's law. I like this one because no fractions. right? Like if you mix up which one of these is in the numerator or denominator, it ruins the whole thing. But this one, everything's in the numerator there. So combining these two, we can get other equations for power. So if power equals current times voltage, and voltage equals current times resistance, then we could substitute IR in for V here and realize that I squared R is one way to think about power. Also, we could plug in V over R in for I, right? So if I is the same thing as V over R, then we get V times V over R or V squared over R. So those three equations for power are good to have committed to memory, right? Because we're given voltage and resistance, it really makes sense to use that equation to calculate power, right? Like we know the voltage, we know the resistance. So that's sort of our way forward here. Let's clean this up a bit. Now let's clean it up a lot. All right, so power equals V squared over R. Calculate the power dissipated. So it's 5 volts squared over 125 ohms of resistance. So we have what 5 squared is 25. 25 over 125 is a fifth. So 0.2. Did I just do some great mental math here? I think I did, class. 0.2. You know, check it in your calculator. You get a calculator, you might as well say, like, oh no, I think that's not too bad, though, right? 25 over 125 is 1/5. 1/5 is 2/10. That's how we read this number, right? 2 in the 10th place, or 2/10 of a watt. Nice. Calculate the percentage uncertainty in the calculated power. All right. So how do we do percentage? Now the power is here, right? So we have to combine uncertainties. There was uncertainty in voltage. So there's the absolute uncertainty. There's the measured value. There was uncertainty in the resistance. There's the percent uncertainty in that. So they give you the percent uncertainty in the resistance, but they give you the absolute uncertainty in the voltage, right? So we have to remember how to calculate the percent uncertainty because we combine percent uncertainties. We add the percentage uncertainty to get the percent uncertainty in the calculated value. So in your calculator, you should take the absolute uncertainty divided by the measured value. The absolute uncertainty in voltage is 0.1 volts divided by the measured value of 5 equals, so 0.02, so that's 2%. There's 2% uncertainty in the voltage. 2% uncertainty. Now remember what we did to calculate power. What we really did was we took V times V over R. And we've talked about this before, and I feel like by now, you know, we've emphasized it enough that no one is going to make the error that students typically make on these calculations, which is where they forget to double count the percent uncertainty in something that's squared. We won't make that mistake, right? We're really focusing on it. So we know that there's 4% uncertainty in power due to the percentage uncertainty in the voltage, plus another 3% from R for a total percent uncertainty of 7%, right? 4 from this, 3 from that, right? So 2 plus 2 is 4, plus another 3 is 7% uncertainty in the calculated power, okay? You have to calculate the percent uncertainty given this data. That's not too bad. Just add it into the percent uncertainty that's reported there. Students that get this wrong probably would report the answer as 5, and they forget to double count the percent uncertainty in volts. So don't make that mistake. Don't be that student. All right, so now we've got to determine the value of the power with its absolute uncertainty to an appropriate number of significant figures. And so we've got the calculated power was 0.2, the percent uncertainty was 7. And so let's take 7% of 0.2. Do that in the calculator also. All right, so we got that. Got my calculated value 0.2 times 0.07. So my absolute uncertainty, 0.2 plus or minus 0.014. So I'm certain in the tenths place. My uncertainty doesn't arrive until the hundredths place out here. Okay. And so we'd round this down. We could really report this, I think, as 0.20 plus or minus 0.01. Okay, so like that's the place value that governs our uncertainty. And so we can report our answer all the way out to the hundredths place, right? Because that's where our uncertainty starts. And so we're plus or minus 0.01 out here in the hundredths place. As we did before, we want to give ourselves immediate feedback and realize we did something wrong right away so we can correct it. We don't want to practice studying the incorrect information. So here we get the moment of truth. Point one. Why did I put? Oh, okay. So here they wrote it like this. So that's exactly what I have here. 0.20 plus or minus 0.01. That's a great way to report it. Or if you want to be a little bit fancier, or I would just say more confusing, you could write it like this: 2.0 plus or minus 0.1 times 10 to the 1. Now that maybe makes more sense if you're dealing with a number that's really small and like, oh, it's just easier to write 10 to the negative 7 over here than like in standard form. So both of these are acceptable ways to report that, but you can see the way that we solved it agrees with what you see in the mark scheme there. So always just sort of go back into the mark scheme and see if that sort of aligns with the working that you've done.